This module is going to be on Introduction to Parallel Programming in OpenMP, and my name is Yogesh Sabharwal. I lead the Cognitive Computing Platforms group at IBM Research India. We basically look at how to optimize scientific applications and algorithms on massively parallel systems. I have done extensive work on parallelization and optimization of scientific applications such as weather modeling codes, finite element analysis, and so on. And also we've looked at optimizing algorithms and benchmarks such as the HPC challenge benchmarks, various graph algorithms, and also deep learning frameworks. So we have expertise in various IBM platforms such as the IBM's Blue Gene supercomputer, the power-based HPC systems, cell processors, and also a lot of parallel programming on GPUs. So what is parallel computing, right? So parallel computing means doing things simultaneously. So what are we doing simultaneously? We might be doing the same thing or something different set of things simultaneously, right? For example, when you are driving a car, right? You might be driving at the same time you might be talking on the phone. Not a great idea, but it might be happening, right? And at the same time you're breathing as well, right? So all these things are happening in parallel. They're happening simultaneously, right? So that is one form of parallel computing. So in this case, what you're doing is different, right? You're doing three different things at the same point in time. Now in different situations, you could be doing the same thing, right? When you're exercising, maybe you're putting your hands up and so on, right? So you're performing the same action in parallel. So when we do things simultaneously, we may be doing the same thing or different things. But what is the important point in parallel computing? We are solving one large problem. I mean, for instance, at this point of time, you are breathing and I might be writing something on a piece of paper, but that we don't generally call that parallel computing because we are completely doing two separate things which are not related to each other at all, right? So in parallel computing, generally we refer to the scenario where we are trying to solve one large problem, and while solving that problem we are doing things simultaneously. Okay. So in serial computing, basically the problem is broken down into a stream of instructions, and then these instructions are executed sequentially one after the other on a single processor, right? And the important point is that only one instruction is executed at a time, at a given point in time, right? And now when you move to parallel computing, what changes? So in parallel computing, the problem is broken down into multiple parts that can be solved concurrently, simultaneously, right? So you have to break down your problem into different parts. And each part now is further divided into a stream of instructions which can be executed on a processor, right? One by one. So the important part over here, what differentiates it from serial computing, is that you are executing different instructions of the different parts simultaneously, right? If you look at galaxies, planetary motions, how the brain functions, how the weather modeling is done, how the traffic moves, right? All of these real world phenomena are parallel by nature, right? So these are complex interrelated events that are happening simultaneously. So it makes sense, if you want to model them, then it makes sense to do the simulation in parallel. And why do we want to use parallel computing? Because first of all, it saves time. We produce the results in reasonable amount of time so that they are useful to us, right? For instance, suppose that we are doing weather modeling. So today when we try to do weather modeling, right, at a good resolution, let's say at a 10 cross 10 kilometer resolution for a region like India, right? Then the weather simulation itself can take, if you run it on a single processor, it can take days to run, right? So what is the point of that? If you are predicting tomorrow's weather and it takes you 3 days to predict that weather, it's of no use to you, right? So you want your results to be useful, and if you can't do them on a serial computer, then you have to basically use parallel computing. But the other issue is that there are many problems that are interesting to scientists and engineers. When you do any simulation, you basically want to do it at a very high resolution, right? So if you want to do it at very high resolution, then there's a lot of data involved, and this data generally doesn't fit in the memory of a single computer, of a PC. So what do? Either you can store it on the secondary storage on the disk and keep on fetching it, and your algorithm has to somehow run in parts, right? Or the other option is that you use a parallel computer. In parallel computing, you have multiple nodes, you have memory associated with every node, and therefore the total memory that is available to you is much larger. So you can load the entire data that you have on the combined memory that the systems have. The other issue is that the processors are not getting any faster. The clock frequency is not improving anymore, and the primary reason is that there are heat dissipation issues and power consumption issues. So what does that mean? That means that you have to resort to parallel computing, right? You're not going to get more speed out of the same processor, so you have to use multiple processors. Where do we use parallel computing? So scientific computing is one huge area where parallel computers are used. This is primarily to solve numerically intensive simulations. So I'll come back to this. This is one of the most important areas. I'll cover this in more detail. But other than this, parallel computing is used heavily in database operations and information systems, right? So for instance, web-based services, they're made scalable. So there are so many requests coming into web servers these days. They have to be load balanced. They have to be sent to different servers. The computations have to be done in parallel. Web search engines, online transaction processing, right? Just imagine the number of requests that credit cards or these other companies that are doing transactions, right? So all of them have to be done in parallel, right? Then there are other systems like client, inventory, database management systems, data mining, online transaction processing, MIS systems, and so on. Then another area is artificial intelligence, machine learning, and deep learning, right? So again, these areas are making heavy use of parallel computing. If you look at something like neural networks, right? So there are lots of nodes which are getting inputs, they are doing some computations, and then producing some new output, which is then consumed by other nodes, right? So it's a graph, layered graph, and lots of nodes are doing computations in parallel. So all of this, is very amenable to parallel computing. And then there are other areas like real-time systems and control applications where this is used heavily. So coming back to scientific computing, right? So that's one of the focus areas where high-performance computing systems or massively parallel systems are majorly used. So for instance, in engineering, right, in car development. So as you know, right, these car companies, they are required to pass certain safety tests. So for instance, they have to ensure that if the car crashes into a wall at a certain speed with a dummy sitting inside the car, what is the impact on the dummy? They have to show that it's limited or no impact. So what does that involve? That actually involves actually crashing the car into a wall. But that is costly, right? If let's say you're trying to build that car, you're not going to crash that car every second day into the wall just to see that whether the dummy is getting hurt or not, right? So again, this is actually done via simulations. So you use parallel computing again because the simulations are very compute intensive and it can take very long. So you want to use parallel computing, and you actually do these simulations on the computers first. And once you're satisfied or you're reasonably sure that it's okay now, that's when you actually take an actual car and go crash it into the wall. Similarly, in aerospace, it's very, very important to understand what is the effect of the wind or turbulence on the wings of an aircraft, right? All of that is done via simulations. In nanotechnology, for material design, for instance, if you're trying to design some glue, you want to figure out what is the right mix of chemicals that you have to use, what are the properties that it will have. A lot of this is done via material design using parallel computing. Disaster prevention and global environment, so things like weather modeling, tsunami prediction, cloud analysis, right? All of these are very compute intensive simulations, right? Involving lots of physical and chemical processes that need to be simulated. Then in life sciences, for drug design and so on, it is used heavily for nuclear reactor analysis. So you want to simulate the nuclear reactions, right? What will happen? In astrophysics, to figure out the formation processes for the Milky Way or the planet formation processes and so on, right? You figure out that these are the laws that should apply, but you want to simulate to figure out that that is actually what happens, right? So these are some of the predominant areas where parallel computing is used in scientific computing. So how do you actually go about using parallel computing in scientific computing? So basically you start with some physical processes, like for instance you want to study the airflow around an airplane, right? And then you build some mathematical models to do the simulation, right? So for instance you model it using Navier-Stokes equations, and then you basically solve that, right? So solving it involves various numerical solutions. So that involves lots of algorithms and using lots of solvers. And that is very, very compute intensive, right? Lots of numerical equations have to be solved. Scientists and engineers are becoming more and more ambitious. So they want to, do it at a very high resolution, with lots of grid points, so that makes it very, very compute intensive. And finally, once the output is produced, you want to visualize that data, and after you validate it, you figure out the physical insights, you may want to go back and modify your models and so on, right? So the numerical solution and the visualization is the part that heavily uses parallel computation, right? So here are some interesting facts about parallel computing. So people actually study they simulate the explosion of a nuclear weapon, and from the moment that the button is pressed to the point that the bomb detonates, actually in real time that happens in few billionths of a second. But if you want to simulate that process, even supercomputers today take weeks to replicate that process. Okay, it's that compute intensive. And another fun fact, Pringle potato chips, right? They have to actually use supercomputing capabilities, parallel computing, to do simulation, what rate to have the assembly line move, because if they move it too fast, then the chips are going to fly off the assembly line, right? So they have to do all those studies, and they do that using supercomputing capabilities.